Stacks are interview catnip. Evaluate reverse Polish notation, RPN, looks tiny, but it reveals whether you truly understand order of operations and data structures. Bong screens love it because one clean stack pass solves everything. No parentheses panic, no precedence chaos. Let's crush it with basic and finish with rock-solid, production-ready code. We're given a list of tokens representing an arithmetic expression in postfix form. Operands are integers. Operators are plus, slash. Evaluate the expression and return an integer, with division truncating towards 0. RPN is tailor-made for a stack. Scan left to right, push numbers. When we see an operator, pop the last two operands, write operand first, apply the operator, and push the result. Single pass, ON time, ON worst case space. Watch the Python gotcha. Integer division must truncate towards 0, use int a, b, not a / b. Plan. Create stack equals. For each token t, if t is an operator, pop b, then a, compute a, t, b, push result. Else, push in t. At the end, top of stack is the result. Let's walk through this solution. The main goal here is simple. Evaluate an arithmetic expression written in reverse Polish notation, postfix. If we try to evaluate left to right without structure, we'll mishandle operator order. If we use a stack and process tokens one by one, everything works smoothly. Approach. Stack evaluation time complexity. ON starts the method that evaluates the expression. Creates a stack to store operands. Iterates through each token in the RPN expression. Handles operators versus numbers. Adds the top two numbers from the stack and pushes the result. Subtracts the second pop number from the first pop number. Multiplies the top two numbers. Divides with correct operand order, A2, B2, integer truncation. If the token is a number, parse and push it onto the stack. End switch, ends loop. Final result is the last number left on the stack. Ends method. And that's how the algorithm works. Efficient, simple, and elegant. Now let's verify the behavior on the provided test case. This RPN expression means 2 plus 1, 3. It matters because the postfix order tests our ability to correctly use the stack to respect operator precedence automatically. Short reasoning. Push 2 push 1. Token plus pop 1 and 2 push 3. Push 3. Token pop 3 and 3 push 9 stack ends with 9. This makes perfect sense because 2 plus 1, 3 equals 9. So our solution checks out, the result matches the expected behavior, and the algorithm handles this test case correctly. Let's walk through this solution. The main goal here is simple. Evaluate a reverse Polish notation expression. If we hardcode operators everywhere, the logic becomes bulky. If we store all operators in a map of functions, everything becomes clean, flexible, and elegant. Approach. Using operator map, functional interface, time complexity, ON starts the RPN evaluation method. Creates a stack to hold numbers during evaluation. Creates a map from operator symbols to actual arithmetic functions. Stores addition logic. Stores subtraction logic. Stores multiplication logic. Stores integer division logic, truncates towards 0. Iterates through each token in the RPN array. Checks if the current token is an operator. Pops operands in correct order. First popped is right operand. Applies the operator function and pushes the result. If token is a number, parse and push it. The final number on the stack is the expression result. Ends method. And that's how the algorithm works. Efficient, simple, and elegant. Now let's verify this solution using the provided test case. This RPN array represents a short expression with both division and addition. It matters because it checks whether our operator map and stack logic correctly handle operator precedence and integer division. Short reasoning. The algorithm pushes numbers until it encounters an operator, then applies the mapped function. 13.5, 2, integer division 4 plus 2 6. Final result on the stack, 6. This is exactly correct for the given RPN expression, confirming that each operator was evaluated in the proper order using the function map. So our solution checks out, the result matches the expected behavior, and the algorithm handles this test case correctly. Ever feel like arithmetic expressions get messy with all the parentheses and operator rules? Evaluate reverse Polish notation flips that chaos into clarity. With one clean stack pass, everything falls neatly into place. No precedence worries, no nested confusion. We're given tokens representing a mathematical expression in postfix form, numbers and operators in sequence. Our goal is to evaluate it and return the final integer result, with division that truncates toward 0. Conceptually, it's about understanding how stacks mirror computation order in a structured, step-by-step way. The beauty of RPN lies in its simplicity. As we scan tokens left to right, numbers are pushed onto a stack. When we hit an operator, we pop the top two numbers, apply the operation, and push the result back. No need for parentheses or operator precedence tables. The key detail: ensure division behaves like real integer truncation toward 0. Here's the logical plan. Initialize an empty stack. For each token, if it's a number, push it. If it's an operator, pop two numbers, right then left, compute, and push the result. At the end, the single value left on the stack is the final answer. We followed that flow precisely. One stack, one pass. The operations handled correctly, especially division truncation. The code ran smoothly on LeetCode without any errors. We validated the logic across multiple test cases, from simple additions to chained multiplications and mixed divisions. Each case matched the expected output: consistent, correct, and efficient. The takeaway? Mastering stack-based evaluation isn't just about RPN, it's about learning to break problems into simple, repeatable actions. Once you see how order unfolds naturally through a stack, complex expressions become effortless to decode.